In the early 19th century, the physical world was filled with forces that could be observed but not fully understood. Electricity and magnetism were among the most puzzling. People had learned how to generate sparks, store charge in Leyden jars, and feel shocks pass through their bodies, yet these experiences felt more like curiosities than parts of a coherent natural law. Magnetism, on the other hand, seemed ancient and almost mystical. Lodestones could attract iron, compass needles could point north, and invisible forces appeared to act across empty space. What troubled scientists was that these forces behaved with remarkable consistency, yet their underlying cause remained hidden. They could be measured, used, and demonstrated, but not truly explained. At that time, physics was transitioning from a descriptive science into a predictive one. Earlier generations of natural philosophers had focused on cataloging phenomena: what happens when amber is rubbed, how iron filings arrange themselves around a magnet, or how sparks jump between conductors. By the mid-1800s, a new ambition had taken hold. Scientists wanted unified principles, mathematical laws that could explain not just one effect, but many at once. Gravity had already provided such an example through Newton's work. Electricity and magnetism, however, stubbornly resisted this kind of unification. They seemed related, but the nature of that relationship was unclear. Experiments showed that electric charges could attract and repel one another, and magnets could do the same with magnetic poles. Yet electric charges could exist alone, while magnetic poles always appeared in pairs. Electric effects could be switched on and off almost instantly, while magnetism often seemed tied to specific materials. These differences made it difficult to believe that the two forces were deeply connected. Many physicists treated them as separate realms, linked only by coincidence or surface similarities. The idea that a single framework might explain both was attractive, but still speculative. The situation began to shift when researchers discovered that electric currents affected magnets. A simple wire carrying current could deflect a compass needle, an observation that shocked the scientific community. For the first time, electricity appeared to influence magnetism directly. This discovery opened a door, but it did not immediately reveal what lay behind it. Was magnetism caused by electricity, or was electricity somehow influenced by magnetism? Or were both manifestations of something deeper still unknown? The experiments answered that something happens, but not why it happens. Adding to the confusion was the concept of motion. In classical mechanics, motion was central. Forces caused objects to accelerate, collide, and change direction. Yet in electricity and magnetism, motion seemed secondary or even irrelevant. Electric charge could sit still on an object and still exert force. A magnet could attract iron filings without anything visibly moving. The idea that motion itself might be essential to these forces was not yet firmly established. Many physicists assumed that the static situation was the fundamental one, and motion was just a convenient way to reveal effects more clearly. In this intellectual climate, theories were often built on incomplete experimental foundations. Mathematical models were proposed, revised, and sometimes abandoned because they lacked direct confirmation. Instruments were improving, but they were still crude by modern standards. Detecting small magnetic fields or subtle electrical effects required patience and ingenuity. Even when experiments were carefully done, their interpretation was open to debate. One scientist's decisive result could be another's ambiguous anomaly. As a result, progress was uneven, advancing in bursts followed by periods of doubt and argument. The deeper philosophical problem was the nature of action at a distance. How could one object influence another without direct contact? Electricity and magnetism both seemed to violate everyday intuition. Invisible forces crossed empty space, acting instantly or nearly so. Some physicists were uncomfortable with this and sought mechanical explanations involving hidden fluids or ether-like substances. Others accepted action at a distance as a fact of nature, but admitted they did not truly understand it. This lack of clarity made it difficult to frame precise questions, let alone design decisive experiments. It was in this uncertain world that the question of electricity, magnetism, and motion took on special importance. If magnetism could be produced by moving charges, then motion was not just an incidental feature, but a fundamental ingredient. This idea hinted at a unifying principle, that electricity at rest and electricity in motion might be two aspects of the same thing, differing only by how charges behave in space and time. Such a view would dissolve some of the apparent contradictions between electric and magnetic phenomena. But without direct proof, it remained an attractive hypothesis rather than an established fact. Many scientists hesitated to pursue this line of thinking because it seemed too abstract or too difficult to test. How could one separate the effects of motion from the effects of current? In most experiments, moving charges meant currents flowing through wires, which introduced complications of resistance, heating, and chemical effects. To isolate motion alone required a level of experimental control that few believed possible. As a result, the idea lingered on the margins of mainstream research, acknowledged but rarely confronted directly. The scientific culture of the time also played a role. Physics was becoming more professional, with reputations built on careful measurement and reproducible results. Risky experiments that challenged accepted views could damage a career if they failed. Many researchers preferred to refine existing theories rather than gamble on radical tests. This conservatism slowed progress but also ensured that when new results did emerge, they were taken seriously. Any claim that motion itself could generate magnetism would have to be supported by exceptionally strong evidence. Despite these obstacles, curiosity continued to drive inquiry. The growing success of mathematical electromagnetism suggested that a deeper unity was within reach. Equations hinted that electric and magnetic fields were intertwined, changing into one another under the right conditions. Still, equations alone could not settle the matter. Nature had to be questioned directly, through experiments that spoke clearly and unambiguously. The challenge was to find a way to ask that question without the usual sources of confusion. This was the world before the rotating disk experiment, a world full of partial insights and unresolved tensions. Electricity and magnetism were powerful tools but poorly understood forces. Motion was central to mechanics but peripheral in electromagnetic thinking. The connections between these ideas were suspected but not demonstrated. Physics stood poised between description and explanation, waiting for an experiment simple enough to be convincing and bold enough to cut through decades of uncertainty. It was into this atmosphere of mystery and anticipation that a carefully chosen question about motion, charge, and magnetism would soon arrive, ready to change how physicists understood the invisible forces shaping the universe. As the 19th century progressed, the mystery surrounding electricity and magnetism deepened rather than disappeared. Each new discovery answered one question while opening several others. Laboratories across Europe and America buzzed with activity. Yet there was a growing sense that something essential was missing. Scientists could describe how electric charges behaved and how magnets influenced materials, but they struggled to explain what these forces truly were. They knew the effects, not the cause. This gap between observation and understanding created an uneasy tension within physics, a feeling that the discipline was standing on the edge of a major breakthrough, without yet knowing how to cross over. One of the most troubling issues was the apparent contradiction between static and dynamic situations. Electric charge at rest produced electric forces, while moving charge in a wire produced magnetic effects. These facts were well established, but they were treated as separate cases. Static electricity belonged to one category, currents to another. The idea that they might be fundamentally the same phenomenon seen from different perspectives was not yet widely accepted. This separation shaped how experiments were designed and how results were interpreted. It limited imagination, because researchers often framed their questions in ways that assumed the distinction was real and unavoidable. At the same time, the concept of fields was still evolving. Today, fields are a central part of physics, but in the early 19th century they were controversial. Many scientists preferred mechanical models, imagining tiny particles, fluids, or vortices filling space and transmitting forces through contact. Fields, by contrast, were abstract and invisible, defined more by mathematics than by physical substance. Electricity and magnetism seemed to demand such abstraction, but accepting it required a shift in thinking that not everyone was ready to make. Without a clear picture of what fields were, it was difficult to understand how motion within them could generate new effects. Measurement also posed serious challenges. Detecting magnetic fields produced by currents was already difficult. Detecting fields produced by subtle forms of motion seemed nearly impossible. Instruments were sensitive but fragile, prone to interference from temperature changes, vibrations, and stray electrical effects. A result could be questioned not because it was wrong, but because it was too small to inspire confidence. This made scientists cautious. Bold claims demanded extraordinary precision, and extraordinary precision was hard to achieve. Despite these difficulties, the intellectual climate was slowly changing. The success of unifying ideas in other areas of physics encouraged researchers to look for deeper connections. Heat, once thought of as a fluid, was increasingly understood in terms of motion at the microscopic level. Light, once mysterious, was being analyzed as a wave phenomenon. These shifts suggested a pattern phenomena that appeared fundamentally different, at first often turned out to be related through motion and energy. It was natural, then, to suspect that electricity and magnetism might follow the same path. This suspicion was reinforced by mathematical developments. Equations describing electric and magnetic effects began to show structural similarities. Terms appeared that linked changes in one quantity to the presence of another. Although these equations were not yet fully unified, they hinted strongly that electricity and magnetism were intertwined aspects of a single system. However, mathematics alone could not convince everyone. Without a clear experimental demonstration, such ideas remained vulnerable to doubt. Physics demanded contact with reality, not just elegant symbols on paper. The broader scientific community was also influenced by practical concerns. Electricity was becoming a technology, not just a curiosity. Telegraph systems were spreading rapidly, transforming communication. Engineers learned how to manipulate currents and magnets to achieve reliable results, even if they did not fully understand the underlying principles. This practical success created a paradox. On one hand, it demonstrated the power of electrical science. On the other, it reduced the urgency of deeper theoretical questions. If devices worked, why worry too much about why they worked? For some, technological progress dulled the drive for fundamental explanation. Yet for others, technology sharpened that drive. The more electricity was used, the more anomalies appeared. Unexpected losses, interference, and unexplained effects hinted that existing theories were incomplete. Engineers encountered problems that could not be solved by trial and error alone. They needed better understanding. This pressure from practice pushed theory forward, demanding answers that went beyond rule-of-thumb explanations. In this way, applied science and pure science began to feed into each other more directly than before. Another important factor was the growing emphasis on experimental rigor. Physics was becoming more exacting, with standards for precision and reproducibility steadily rising. A convincing experiment had to isolate variables, eliminate alternative explanations, and produce results that others could confirm. This culture of rigor made it harder for speculative ideas to survive without evidence, but it also meant that when evidence did appear, it carried great weight. A single well-designed experiment could reshape an entire field. The question of motion became increasingly central within this framework. Motion was measurable, controllable, and deeply rooted in physical intuition. If magnetism could be tied directly to motion, the mysterious nature of magnetic forces might be reduced to something more familiar. Motion had already explained heat and sound. Perhaps it could explain magnetism as well. This possibility was intellectually appealing because it promised continuity rather than fragmentation. It suggested that nature used the same basic principles in many different contexts. Still, the path forward was unclear. How could one design an experiment that involved motion of charge without introducing currents in the conventional sense? Most existing setups relied on wires, batteries, and chemical reactions. These elements brought along unwanted complications. To test the role of motion alone, one would need a system in which charge moved purely because of mechanical motion, not because of an applied voltage. This requirement narrowed the field of possibilities dramatically and discouraged many would-be experimenters. The hesitation was not just technical but psychological, challenging an implicit assumption that magnetism required currents in wires meant risking error and criticism. Scientific communities, like all human groups, develop shared expectations about what is reasonable. Ideas that fall outside those expectations face higher barriers. Even when such ideas are logically sound, they must overcome inertia and skepticism. This social dimension of science often determines which questions are asked and which are left unexplored. Yet the very presence of these barriers made the unresolved questions more compelling. The gap between what was known and what was suspected created a sense of unfinished business. Electricity and magnetism seemed too closely related to remain partially understood. The hints provided by theory, technology, and analogy all pointed in the same direction. Something fundamental was waiting to be uncovered, something that would clarify why these forces behaved as they did. Thus, before the decisive experiment ever took place, physics was already primed for change. The old view of electricity and magnetism as separate, almost unrelated phenomena was growing unstable. Motion, once considered secondary, was emerging as a possible key. Fields, once controversial, were gaining acceptance as useful tools for thinking about invisible forces. The stage was set not by a single idea, but by a convergence of doubts, hints, and unmet expectations. In this atmosphere, a carefully conceived experiment could have an outsized impact. It would not merely add another fact to the growing list of observations. It would resolve a tension that had been building for decades. By addressing the role of motion directly, such an experiment could transform vague suspicion into concrete knowledge. It could turn a philosophical question into an empirical one and provide a clear answer that theory alone could not supply. This is why the world before the rotating disk was not just ignorant, but restless. Physics knew enough to realize that it did not yet understand its own foundations. Electricity and magnetism were powerful, mysterious, and partially unified forces waiting for a decisive demonstration. The first keynote, this world of uncertainty and anticipation, is essential to understanding why a simple experiment with motion and charge would later resonate so deeply. It was not just about discovering something new, it was about finally bringing clarity to a landscape long clouded by incomplete ideas and unanswered questions. The idea that a simple rotating disk could challenge accepted physics sounds almost unbelievable when viewed from a modern perspective. Today, we associate revolutions in science with complex machinery, massive accelerators, or advanced mathematics. In the 19th century, however, the most disruptive experiments were often built from ordinary objects arranged in extraordinary ways. The rotating disk belonged to this tradition. It was simple not because the question behind it was simple, but because it stripped the problem down to its bare essentials. That simplicity was precisely what made it so threatening to established assumptions. At the time, the dominant image of electromagnetic phenomena was shaped by wires, currents, and circuits. Electricity was thought of as something that flowed through conductors, driven by batteries or chemical reactions. Magnetism appeared when that flow occurred. This picture had become so familiar that it was rarely questioned. Textbooks, lectures, and laboratories were organized around it. Students learned that if you wanted magnetism, you needed a current. The idea was practical, intuitive, and reinforced by countless demonstrations. A rotating disk, carrying charge but not acting as a conventional circuit, did not fit comfortably into this framework. The disk itself was an unassuming object. It had no coils, no switches, no visible source of electrical flow. When stationary, it behaved exactly as expected, a charged object producing electric effects and nothing more. No magnetism appeared, no compass needle moved. According to conventional thinking, this was the end of the story. Charge at rest belonged to electrostatics, a domain considered fundamentally separate from magnetism. The shock came from asking what would happen if that same charge were set into motion without becoming a current in the usual sense. Rotation introduced a subtle but profound change. Every bit of charge on the disk moved in a circular path. There was no start or end point, no net flow from one place to another, yet motion was undeniably present. This situation did not align with the established categories of physics. It was neither static electricity nor an electric current in a wire. It occupied an awkward middle ground that theory had not fully addressed. The rotating disk forced physicists to confront this gap directly. What made the disk so challenging was not just its motion, but the kind of motion it embodied. Circular motion is continuous and self-contained. Charges did not pile up at one end or dissipate at another. They simply kept moving endlessly as long as the disk rotated. This raised an uncomfortable question. If magnetism depended on current, and current depended on charge flow, what exactly counted as flow? Was flow defined by direction, by path, or by the mere fact of movement? The rotating disk exposed the ambiguity in these definitions. Many physicists initially dismissed the idea that such a system could produce magnetism. They assumed that any observed magnetic effect must come from unintended currents or experimental artifacts. This skepticism was understandable. The prevailing theories had worked well in countless other contexts. To abandon them because of a spinning disk seemed premature. Yet the very act of dismissing the disk revealed how deeply ingrained certain assumptions had become. The disk did not violate known laws outright. Instead, it revealed that those laws were framed too narrowly. The challenge posed by the rotating disk was conceptual before it was experimental. It asked physicists to reconsider what they meant by electric current. In everyday language, current suggested something flowing from one place to another, like water in a pipe. But in physics, current is more precisely defined as the movement of charge. The disk took this definition seriously and pushed it to its logical conclusion. If charge moved even in circles, should that not count? The disk insisted on clarity where vague intuition had previously sufficed. This insistence was unsettling. Physics had long relied on idealized models that worked well within their intended scope. The rotating disk fell just outside that scope, where the models blurred. Accepting its implications meant admitting that familiar categories were incomplete. It suggested that magnetism was not tied to specific devices like wires, but to a more abstract principle involving motion. Such a shift threatened to reorganize how electromagnetic phenomena were taught and understood. The simplicity of the disk amplified its impact. Had the experiment involved complex apparatus, critics could have blamed the results on hidden variables or obscure interactions. The disk offered no such refuge. Its behavior could be visualized easily. Anyone could understand that the charges on its surface were moving. If magnetism appeared, the explanation had to confront that motion directly. This transparency made the experiment both powerful and dangerous to established views. The rotating disk also challenged the separation between mechanical motion and electrical phenomena. Traditionally, these domains were studied somewhat independently. Mechanics dealt with masses, forces, and motion. Electricity dealt with charge, potential, and current. The disk blurred this boundary. Mechanical rotation directly influenced an electromagnetic outcome. This connection hinted at a deeper unity between physical laws, one that went beyond convenience and into necessity. It suggested that motion, regardless of context, had electromagnetic consequences. Another reason the disk was so disruptive was its universality. It did not rely on special materials or exotic conditions. Any charged disk, in principle, should behave the same way. This universality made the result hard to dismiss as a curiosity. If true, it applied broadly, not just to a single experimental setup. It implied that similar effects might occur wherever charges moved, including in systems not yet fully explored, such as within atoms or celestial bodies. The resistance to the disk's implications also reflected a broader tension in science between intuition and formal definition. Intuition often lags behind theory, especially when phenomena are invisible. Magnetism had always been invisible, inferred from its effects. The idea that motion alone, without visible current, could generate it ran counter to everyday experience. Yet physics has often advanced by moving beyond intuition, guided instead by careful reasoning and evidence. The rotating disk demanded exactly this kind of intellectual leap. The disk also highlighted the importance of asking unconventional questions. The question was not whether currents produce magnetism, which was already known, but whether motion itself was the essential ingredient. This shift in emphasis changed the entire problem. It reframed magnetism not as a property of certain devices, but as a consequence of a more general condition. Such reframing is rare and difficult, because it requires seeing past familiar patterns to underlying principles. In hindsight, the rotating disk appears almost inevitable, a natural step in the progression of electromagnetic theory. At the time, however, it felt risky and unnecessary to many. Physics seemed to function well enough without it. Yet this apparent sufficiency was deceptive. Without confronting the disk's challenge, the field would have remained fragmented, with separate rules for static and dynamic cases. The disk exposed the artificial nature of that division. The simplicity of the rotating disk thus became its greatest strength. It forced clarity. It refused to hide behind complexity. It asked a single, precise question and demanded a clear answer. In doing so, it destabilized comfortable assumptions and opened the door to a more unified understanding of electromagnetism. The second keynote is therefore not just about an object, but about the power of simplicity to reveal hidden weaknesses in accepted ideas. A plain disk, spinning quietly, confronted physics with its own definitions and asked whether they were truly complete. The deeper the implications of the rotating disk were considered, the more it became clear that its challenge extended beyond a single experimental result. It questioned the mental habits physicists had developed over decades. Science often advances by building stable categories, and once those categories prove useful, they harden into assumptions. Electricity belonged to one category, magnetism to another, and mechanical motion to a third. The rotating disk quietly refused to respect these boundaries. It behaved as if nature itself did not recognize the divisions physicists had imposed. One of the most uncomfortable realizations was that the disk exposed a hidden circularity in earlier explanations. Physicists said that currents produced magnetism, but when asked what a current truly was, the answer reduced to moving charge. The disk simply removed the extra structure of wires and circuits and presented moving charge in its purest form. This made it difficult to maintain the older distinction without redefining terms in an artificial way. Either motion of charge mattered, or it did not. The disk forced a choice that theory had long postponed. This realization also brought attention to the role of reference frames, even though relativity had not yet fully emerged. Motion is not absolute, it is always measured relative to something else. If magnetism arises from moving charges, then magnetic effects might depend on the observer's frame of reference. This idea was deeply unsettling at the time because physics still leaned heavily on absolute notions of space and rest. The rotating disk hinted, indirectly, that electromagnetic phenomena might be more subtle than previously thought, sensitive to how motion itself was described. The disk also compelled physicists to think differently about symmetry. A stationary charged disk is symmetric in every direction. Nothing distinguishes one side from another. Once it rotates, that symmetry is broken. There is a preferred direction of motion, a sense of rotation. The emergence of magnetism in this situation suggested that magnetic fields were closely tied to broken symmetry caused by motion. This was a new way of thinking, one that shifted focus from static properties to dynamic processes. Magnetism was no longer something an object simply had, It was something that emerged from how charge moved. Another unsettling aspect was the continuity implied by the disk. There was no sudden jump from non-magnetic to magnetic behavior. As the disk began to rotate, the magnetic effect grew gradually. Faster rotation produced stronger effects. This smooth transition undermined the idea that magnetism was a separate phenomenon switched on only under special conditions. Instead, it appeared as a continuous extension of electric behavior. Such continuity is a hallmark of deep physical laws, but recognizing it required abandoning older, more compartmentalized thinking. The rotating disk also challenged the notion that experimental importance scales with complexity. Many believed that only intricate apparatus could probe fundamental laws. The disk contradicted this belief. Its power lay not in technological sophistication, but in conceptual precision. This served as a reminder that the most profound experiments often arise from asking the right question, not from building the most elaborate machine. The disk became an example of how simplicity can expose truths that complexity sometimes obscures. As discussion spread, the disk began to influence how physicists thought about other systems. If a rotating charged disk could produce magnetism, what about rotating charged spheres, rings, or even planets? Could celestial bodies generate magnetic fields through similar mechanisms? These questions expanded the disk's relevance far beyond the laboratory. It suggested that magnetism might be a natural consequence of motion on many scales, from the microscopic to the astronomical. This universality made the challenge impossible to ignore. The disk also encouraged a shift away from substance-based explanations. Earlier theories often relied on imagined fluids or magnetic matter circulating inside objects. The rotating disk made such ideas seem increasingly unnecessary. There was no need to invoke hidden substances when motion of charge sufficed. This aligned with a broader trend in physics, moving away from mechanical analogies toward more abstract but powerful principles. Fields and motion began to replace fluids and particles as the primary explanatory tools. Resistance to this shift did not vanish overnight. Some physicists attempted to reinterpret the disk's implications in ways that preserved older frameworks. They proposed that microscopic currents must be present, or that the effect was somehow indirect. While these interpretations were not entirely unreasonable, they grew increasingly strained as evidence accumulated. Each attempt to preserve the old picture added complexity without increasing explanatory power. Gradually, the simpler view gained ground. Motion of charge itself was fundamental. The educational impact of this realization was also significant. Once magnetism was understood as arising from moving charge, teaching electromagnetism became more coherent. Concepts that had seemed disconnected could be linked by a common thread. Students could be shown that static electric fields, currents, and magnetic fields were not isolated topics, but parts of a single story about charge and motion. The rotating disk played a quiet but crucial role in making this narrative possible. The disk further highlighted the importance of experimental humility. It reminded physicists that nature does not always conform to the categories humans find convenient. When experiments reveal inconsistencies, it is often the categories, not nature, that must change. This lesson resonated beyond electromagnetism. It reinforced a general principle of scientific progress: definitions and concepts are tools, not truths. When they stop working, they must be revised or abandoned. Another subtle but profound implication concerned causality. In the old view, current caused magnetism as a kind of secondary effect. The disk suggested a more direct relationship. Motion was not merely correlated with magnetism, it was its cause. This sharpened the causal structure of electromagnetic theory. Instead of treating magnetism as an add-on, it became an inevitable outcome of moving charge. Such clarity strengthened the theoretical foundations of the field. The rotating disk also contributed to a growing appreciation of experimental boundary cases. Often, the most informative experiments are those that sit at the edge of established theory, where definitions become ambiguous. The disk occupied exactly such a boundary. It was neither purely static nor conventionally dynamic. By exploring this gray area, physicists gained insight into the structure of their theories. Boundary cases, once seen as nuisances, began to be valued as opportunities for discovery. Over time, the conceptual challenge posed by the rotating disk was absorbed into mainstream physics. What once seemed radical became obvious in hindsight. Magnetism as a consequence of moving charge is now a standard idea, taught early and rarely questioned. Yet this familiarity should not obscure how disruptive the idea once was. It required a rethinking of deeply held assumptions and a willingness to let go of comfortable distinctions. The second keynote, centered on the simple rotating disk, is therefore about more than an object or an experiment. It is about how simplicity can destabilize entrenched ideas, how motion can reveal hidden unity, and how physics advances not only by adding new facts, but by reorganizing old ones. The disk did not merely add magnetism to a list of phenomena, it redefined what magnetism meant. By doing so, it quietly but decisively changed the course of electromagnetic thought, proving that even the most familiar concepts can be transformed by a single, well-chosen question. Henry Augustus Rowland entered the story of electromagnetism not as a revolutionary intent on overturning established theory, but as a careful experimentalist guided by a deep sense of physical clarity. His question about motion, charge, and magnetism did not arise from speculation alone. It grew out of a disciplined engagement with the unresolved problems of his time. Rowland belonged to a generation of physicists who believed that nature would yield its secrets only to those willing to combine conceptual boldness with experimental restraint. He was not interested in dramatic claims, he was interested in decisive answers. Rowland's background shaped his approach. Trained in an era when precision measurement was becoming the hallmark of serious physics, he developed a strong respect for accuracy and reproducibility. He understood that controversial ideas required especially strong evidence. This understanding guided the way he framed his central question. Instead of asking whether electricity and magnetism were related in some vague sense, he focused on a sharply defined issue: does the motion of electric charge, by itself, produce magnetism? This question was narrow enough to be tested and broad enough to have far-reaching consequences. The intellectual context of Rowland's work was marked by both progress and confusion. Theoretical advances suggested deep connections between electric and magnetic phenomena, but experimental confirmation lagged behind. Many physicists were content to rely on indirect evidence, trusting that mathematics would eventually justify itself. Rowland was not satisfied with this approach. He believed that theory and experiment should advance together, each correcting and refining the other. If a theoretical idea could not be tested, its status remained uncertain. For Rowland, uncertainty was an invitation to design better experiments. His attention turned to the nature of electric current. In most laboratory setups, current was inseparable from wires, batteries, and chemical reactions. These elements made it difficult to isolate what truly mattered. Was magnetism produced by the chemical processes in a battery, the structure of a wire, or the movement of charge itself? Rowland suspected the last option, but suspicion was not enough. He wanted an experiment in which motion could be introduced without the usual accompaniments of current. Only then could the essential factor be identified. This led him to consider mechanical motion as a way of moving charge. A charged object set into motion carried its charge with it. Unlike current in a wire, this motion did not depend on a potential difference or a closed circuit. It was purely kinematic. The idea was deceptively simple, yet it required a willingness to think outside established experimental traditions. Most physicists were accustomed to electrical apparatus, not rotating machinery. Combining the two demanded both creativity and confidence. Rowland's question was radical in its implications, but conservative in its formulation. He did not claim that existing theories were wrong. Instead, he asked whether they were incomplete. This distinction mattered. By framing his work as an extension rather than a rejection, he made it easier for the scientific community to engage with his results. He positioned himself not as an iconoclast, but as someone filling a gap in understanding. This strategic modesty played a role in how his work was eventually received. Designing the experiment required careful consideration of potential objections. Rowland anticipated that critics would attribute any observed magnetic effect to stray currents or experimental flaws. To address this, he focused on controlling every aspect of the setup. He paid close attention to insulation, grounding, and symmetry. He chose materials and configurations that minimized unwanted effects. His goal was not just to detect magnetism, but to make alternative explanations increasingly implausible. The choice of a rotating disk was particularly insightful. A disk allowed for uniform circular motion, ensuring that the movement of charge was well defined. Every part of the disk moved with a predictable velocity, making the system easier to analyze conceptually. This uniformity also helped in interpretation. If magnetism appeared, it could be linked directly to the rotational motion, not to irregularities in the setup. The disk became a controlled environment in which motion was the only new variable. Rowland's question also reflected a philosophical commitment to clarity. He believed that physical concepts should be defined in ways that corresponded to measurable realities. If magnetism depended on current, and current was defined as moving charge, then magnetism should depend on moving charge, regardless of how that motion was produced. Any definition that excluded certain kinds of motion was, in his view, arbitrary. The rotating disk was a way to test whether physics lived up to its own definitions. This approach revealed Rowland's sensitivity to hidden assumptions. He recognized that scientists often rely on implicit ideas without realizing it. In this case, the assumption was that current meant flow through a conductor. Rowland saw that this was a historical convenience, not a logical necessity. By challenging this assumption, he aimed to refine the conceptual foundations of electromagnetism. His work exemplified how progress sometimes comes not from discovering new phenomena, but from questioning how old ones are defined. The courage of Rowland's question should not be underestimated. Even a carefully framed experiment risked failure or misinterpretation. A negative result could have reinforced existing views and sidelined the question for years. Yet Rowland accepted this risk. He understood that science advances through such risks, and that avoiding them leads to stagnation. His willingness to test a fundamental idea experimentally reflected a deep confidence in the scientific method. Rowland's work also highlighted the importance of independence in research. At the time, scientific communities were often influenced by dominant figures and prevailing theories. Challenging these required not only intellectual insight but personal resolve. Rowland pursued his question despite uncertainty about how it would be received. This independence allowed him to explore a path others might have avoided, opening new territory for investigation. In focusing on motion, Rowland was also anticipating future developments. Although he could not have foreseen the full implications, his question pointed toward a more dynamic view of electromagnetic phenomena. It suggested that fields and forces were not static entities, but emerged from motion and interaction. This perspective would later become central to modern physics, influencing ideas about relativity and field theory. In this sense, Rowland's question was ahead of its time. The third keynote, centered on Rowland's question, is therefore about the power of asking precisely the right thing. It shows how a well-formulated question can cut through confusion and guide experimental design. Rowland did not attempt to explain everything at once. He isolated a single issue and pursued it with rigor. This focus allowed him to produce a result that was both specific and transformative. His question turned motion from a background detail into a central feature of electromagnetic theory, setting the stage for a decisive experimental test that would soon follow. As Rowland refined his question, he became increasingly aware that its significance extended beyond the immediate issue of magnetism. What he was really probing was the relationship between physical definitions and physical reality. Science often advances by naming things, but names can mislead when they become substitutes for understanding. The term electric current had acquired a life of its own, suggesting a distinct entity rather than a description of behavior. Rowland sensed that this linguistic habit had quietly shaped how physicists thought, narrowing the range of acceptable explanations. His question was an attempt to peel away that habit and look directly at what was happening in nature. This sensitivity to language and definition placed Rowland in a tradition that valued conceptual hygiene. He believed that if two situations were physically equivalent, they should be treated the same by theory. Moving charge in a wire and moving charge on a rotating object were, at a fundamental level, both examples of charge in motion. If theory treated them differently, then theory was drawing distinctions that nature did not. This conviction gave his work a quiet philosophical depth. He was not merely testing an effect, he was testing whether physics was being honest with itself. Rowland also understood that asking the right question meant knowing what not to ask. He did not ask whether the rotating disk could be useful, or whether it resembled existing devices. Such questions would have distracted from the core issue. Instead, he focused relentlessly on causation. What, precisely, causes magnetism? Is it a particular arrangement of matter, or is it motion itself? By stripping the problem to this level, he avoided the trap of accidental complexity. Every element of his thinking served the central aim of isolating cause from context. The clarity of his question influenced the discipline of experimental design. Rowland's planning was guided by a kind of intellectual minimalism. He sought the simplest possible system in which the question could be meaningfully asked. This simplicity was not a lack of ambition, but a strategic choice. The fewer moving parts in the apparatus, the fewer places for doubt to hide. His question demanded an experiment that could speak clearly, without ambiguity, and simplicity was the best way to achieve that. Rowland's mindset also reflected a broader shift in how physicists approached foundational issues. Earlier generations often relied on speculative models, imagining unseen mechanisms to account for observed effects. Rowland belonged to a newer generation that placed greater trust in operational definitions and measurable quantities. For him, the meaning of a concept was tied to how it could be tested. If magnetism was defined by measurable magnetic fields and motion by measurable velocities, then their relationship had to be explored in measurable terms. Anything else risked drifting into metaphysics. This approach made his work resilient to criticism. Critics could challenge the interpretation of results, but they could not easily challenge the relevance of the question itself. The question was grounded in definitions everyone accepted. Charges move. Magnetic fields can be detected. Does one follow from the other? This framing gave Rowland's work a kind of inevitability. Even those who doubted his conclusions had to admit that the question deserved an answer. Rowland's question also revealed a deep respect for the continuity of physical law. He did not believe that nature behaved differently in different experimental contexts without reason. If motion mattered in one case, it should matter in others. This belief guided his insistence that mechanical motion and electrical phenomena be considered together. It was a unifying instinct seeking coherence rather than compartmentalization. Such instincts often drive major advances because they resist the temptation to accept fragmented explanations. There was also an element of patience in Rowland's approach. He understood that a question of this depth could not be answered quickly or casually. It required careful preparation, repeated trials, and a willingness to revise assumptions. He was prepared for the possibility that the answer might be subtle or even disappointing. Yet he pursued it anyway, trusting that clarity, even if it contradicted expectations, was preferable to comfortable confusion. The broader scientific community, though not always aware of it, benefited from this patience. Rowland's question acted as a focusing lens, bringing into sharper relief issues that had been blurred by habit and tradition. It encouraged others to think more carefully about what they meant by current, motion, and magnetism. Even before the experiment was completed, the question itself began to reshape discussions. It highlighted weaknesses in existing explanations and suggested new directions for inquiry. In retrospect, Rowland's question can be seen as a turning point not because it introduced a new concept, but because it clarified an old one. Motion had always been present in discussions of current, but it had been treated as incidental. Rowland elevated it to center stage. By doing so, he changed the narrative of electromagnetism from one about special arrangements and devices to one about fundamental processes. This shift in emphasis would prove crucial for later developments, including the field-based view of electromagnetism and, eventually, relativistic interpretations. The courage of Rowland's inquiry lay in its restraint. He did not overstate its importance or promise sweeping conclusions. He trusted that a well-posed question, honestly pursued, would speak for itself. This trust is a hallmark of mature science. It reflects confidence not in personal insight alone, but in the capacity of nature to answer when questioned properly. Rowland's work exemplified this attitude, reminding physics that progress depends as much on the quality of questions as on the brilliance of answers. Thus, the third keynote reaches beyond the figure of Rowland himself. It illustrates how scientific revolutions often begin quietly, with a single question carefully sharpened against the grindstone of definition and measurement. Before any disk was set spinning, before any magnetic needle trembled, the true breakthrough had already occurred. It happened in the act of asking whether motion alone could give rise to magnetism. That question reshaped the landscape of electromagnetism, preparing it for an experiment that would confirm what careful reasoning had already begun to reveal. The moment Henry Rowland carried his idea into the laboratory, the abstract question about motion and magnetism was transformed into a concrete encounter with nature. This stage marked a decisive shift from speculation to demonstration. The experiment itself was not dramatic in appearance, yet it carried enormous conceptual weight. It was designed to let motion speak for itself, without interference from the familiar mechanisms of electrical circuits. In doing so, it aimed to reveal whether nature truly cared about how charge moved or only about the devices humans used to move it. At the heart of the setup was the charged rotating disk. Once electrically charged, the disk behaved exactly as electrostatics predicted when it was still. No magnetic effects could be detected. This initial state was crucial because it established a clear baseline. Any later change could be attributed not to the presence of charge alone, but to something new introduced into the system. That new element was motion. When the disk began to rotate, every bit of charge on its surface entered into continuous circular motion. Nothing else about the system changed. No wires were connected, no batteries were activated, and no currents in the conventional sense were introduced. As the disk spun, sensitive magnetic detectors were brought into play. These instruments were capable of registering extremely weak magnetic fields far smaller than those produced by everyday magnets. Rowland understood that the expected effect, if it existed at all, would be subtle. The strength of the experiment lay not in producing a large signal, but in producing a clean one. Even a faint magnetic response would be meaningful if it could be traced unambiguously to the rotation of charge. When the disk reached steady rotation, the magnetic instruments responded. The deflection was small, but it was consistent and repeatable. When the rotation stopped, the effect disappeared. When the direction of rotation was reversed, the direction of the magnetic effect reversed as well. This behavior mirrored what was already known about currents in wires, yet it occurred in a system without a traditional current. The implication was unavoidable. Motion of electric charge, regardless of the form it took, produced magnetism. What made this result so powerful was its clarity. There was no sudden jump, no threshold effect. The strength of the magnetic response increased smoothly with the speed of rotation. Faster motion led to stronger magnetism. This continuous relationship reinforced the idea that magnetism was not a separate phenomenon that switched on under special circumstances, but a natural consequence of motion. The experiment revealed magnetism as an emergent property arising directly from the dynamics of charge. Skepticism was inevitable, and Rowland anticipated it. He repeated the experiment under varying conditions, adjusting the amount of charge, the speed of rotation, and the geometry of the setup. Each variation told the same story. The effect persisted, scaled predictably, and vanished when motion ceased. By systematically ruling out alternative explanations, Rowland strengthened the causal link between motion and magnetism. The experiment did not rely on a single observation, but on a pattern of behavior that could not be dismissed as coincidence. This stage of the work represented a turning point because it translated a conceptual suspicion into empirical fact. Before this, the idea that motion alone could generate magnetism was plausible but unproven. After the experiment, it became an observed feature of the physical world. The rotating disk did not merely support existing theory, it clarified it. It showed that what mattered was not the presence of a circuit, but the movement of charge through space. The broader significance of the experiment lay in how it reframed the understanding of electromagnetic phenomena. It suggested that the distinction between static electricity and magnetism was not fundamental, but contextual. Static situations were simply cases where charges were not moving. Dynamic situations, whether in wires or rotating objects, revealed magnetic effects because motion was present. This insight simplified the conceptual landscape of electromagnetism, replacing a patchwork of special cases with a unified principle. Equally important was the experimental style itself. The rotating disk demonstrated the power of minimalism in science. By removing unnecessary elements, it allowed the essential relationship to emerge clearly. The experiment did not overwhelm theory with complexity, it disciplined theory by forcing it to confront a simple fact. In this sense, the experiment was not just a test of a hypothesis, but a lesson in how to interrogate nature effectively. The fourth keynote captures this moment of transformation, when movement was conclusively shown to be a magnetic source. It marks the instant when motion ceased to be a background detail and became a causal agent. The rotating disk turned an abstract idea into a physical reality, proving that magnetism could be born directly from motion. In doing so, it reshaped the understanding of electromagnetism and demonstrated how a carefully crafted experiment can illuminate principles that had long remained hidden in plain sight. When the results of the rotating disk experiment began to circulate, they did not enter a vacuum of open acceptance. Instead, they collided with a scientific culture trained to be cautious, critical, and often skeptical. This response was not a flaw in science but one of its defining strengths. Extraordinary claims, especially those that threaten established understanding, demand extraordinary scrutiny. Rowland's findings were no exception. The idea that simple motion of charge could generate magnetism without a conventional current challenged habits of thought that had been reinforced for decades. Initial reactions ranged from curiosity to outright doubt. Some physicists questioned whether the magnetic effect was real or merely an artifact of the experimental setup. Others suspected that hidden currents must be flowing somewhere, perhaps through the air, the supports of the apparatus, or imperfections in insulation. These objections were not unreasonable. In an era when instruments were sensitive but still imperfect, subtle effects were often vulnerable to misinterpretation. Critics demanded proof that every alternative explanation had been excluded. Rowland responded to this skepticism not with defensive argument but with methodical verification. He refined his apparatus, improved insulation, and altered experimental conditions to test each objection in turn. If critics suggested that air currents might be responsible, he modified the environment. If they proposed that leakage currents were at work, he redesigned the supports and repeated the measurements. Each refinement strengthened the conclusion. The magnetic effect followed the rotation of the charged disk and nothing else. When the disk stopped, the effect vanished. When the direction of rotation changed, the magnetic response changed accordingly. These consistent correlations were difficult to explain away. The process of verification extended beyond Rowland's own laboratory. Other physicists attempted to replicate the experiment, sometimes with different equipment or alternative measurement techniques. Replication was essential because it removed the possibility that the results were tied to one individual's methods or biases. As confirmations accumulated, skepticism gradually shifted in tone. What began as doubt turned into careful consideration. Critics no longer asked whether the effect existed, but how best to interpret it. This period of scrutiny revealed an important feature of scientific progress. Acceptance rarely comes from a single decisive moment. Instead, it emerges through repeated confrontation between claim and criticism. Each challenge forces the evidence to become stronger and the interpretation clearer. In this sense, skepticism was not an obstacle to Rowland's work, but a catalyst that refined it. The rotating disk experiment gained credibility precisely because it survived sustained examination. The debate also exposed deeper theoretical tensions. Some physicists accepted the experimental result but resisted its broader implications. They tried to fit the rotating disk into existing frameworks by reinterpreting it in familiar terms. For example, they suggested that microscopic currents within the disk might be responsible, preserving the traditional link between current and magnetism. While such interpretations were not entirely wrong, they gradually appeared unnecessary. The simpler explanation, that motion of charge itself produced magnetism, accounted for the observations without added assumptions. This struggle over interpretation highlighted the difference between accommodating a result and understanding it. It is often easier to adjust theory superficially than to rethink foundational concepts. The rotating disk forced a choice between complexity and clarity. Over time, clarity prevailed. Physicists recognized that the experiment did not require exotic mechanisms or hidden processes. It revealed a straightforward causal relationship that theory could and should embrace. The episode also underscored the social dimension of science. Acceptance depended not only on data but on trust in methods, reputation, and transparency. Rowland's meticulous approach earned respect, making it easier for others to take his results seriously. His willingness to share details and invite replication reinforced confidence. This openness was crucial in transforming a controversial finding into accepted knowledge. As skepticism softened, the rotating disk began to appear less as a challenge and more as a confirmation of emerging theoretical ideas. It aligned with mathematical descriptions that treated electric and magnetic fields as interconnected. The experiment provided a physical anchor for these abstractions, grounding them in observable reality. What had once seemed speculative gained the solidity of empirical support. The fifth keynote captures this phase of resistance and resolution. It shows how scientific truth is not declared but negotiated through evidence and critique. Skepticism tested the rotating disk experiment from every angle, and the experiment endured. In doing so, it earned its place in physics. The journey from doubt to acceptance was not just about proving a result, but about strengthening the culture of inquiry that makes such proof meaningful. Through verification and debate, the rotating disk moved from a surprising claim to a trusted insight, reshaping how physicists understood the relationship between motion, charge, and magnetism. Once the rotating disk experiment had survived skepticism and verification, its influence began to spread into the broader structure of electromagnetic theory. The result did not stand alone as an isolated curiosity. It demanded to be integrated into the way physicists thought about electricity and magnetism as a whole. This integration marked a decisive stage in the evolution of physics because it shifted emphasis from devices and materials to principles and processes. Magnetism was no longer treated as something special that appeared only in certain arrangements, but as a natural consequence of motion. The experiment strengthened the emerging idea that electric and magnetic phenomena were two expressions of a single underlying reality. If magnetism could be produced by moving charge in any form, then the distinction between static electricity and magnetism became one of circumstance rather than kind. Static situations were simply those in which charges were not moving. Dynamic situations revealed magnetic effects because motion was present. This perspective brought coherence to a field that had long been fragmented by separate rules and exceptions. Rowland's result also provided crucial support for field-based descriptions of electromagnetism. Fields had been introduced as mathematical tools, but their physical meaning was still debated. The rotating disk made it clear that changes in motion altered the surrounding magnetic field in predictable ways. This reinforced the idea that fields were not abstract bookkeeping devices, but real entities that responded to the behavior of charges. The disk demonstrated that by controlling motion, one could shape the field itself. Theoretical developments soon reflected this shift. Equations describing electromagnetic phenomena began to emphasize the role of moving charges more explicitly. Magnetism was understood not as an independent force, but as an effect arising from electric charges in motion. This view reduced the number of fundamental assumptions required to explain observations. Instead of postulating separate origins for electric and magnetic forces, physics could describe both using a common framework centered on charge and motion. The experiment also influenced how physicists thought about symmetry and transformation. It suggested that electric and magnetic effects could transform into one another depending on how charges moved. This idea, still in an early form, hinted at a deeper symmetry underlying electromagnetism. Although the full implications would only become clear later, the rotating disk contributed to the intuition that electricity and magnetism were not fixed categories, but aspects of a single phenomenon seen under different conditions. Beyond theory, the result reshaped experimental practice. Physicists became more attentive to the role of motion in systems previously considered static. Rotating conductors, moving charges, and dynamic configurations gained new significance as sources of magnetic effects. The disk encouraged researchers to look for magnetism in unexpected places, broadening the scope of investigation. This expansion enriched the field, leading to new experiments and insights. The influence of Rowland's work extended into education as well. Teaching electromagnetism became more conceptually unified. Students could be shown that magnetism did not require special materials or mysterious properties. It arose whenever charges moved. This clarity made the subject more coherent and intellectually satisfying. The rotating disk thus played a quiet but important role in shaping how generations of physicists learned to think about electromagnetic phenomena. Perhaps most importantly, the experiment helped establish a style of explanation that valued underlying mechanisms over surface descriptions. Instead of saying that wires produce magnetism, physicists could say that moving charges do. This shift in language reflected a deeper shift in understanding. It replaced a device-centered view with a process-centered one. Such shifts are often subtle, but they mark real progress in science because they align explanation more closely with cause. The sixth keynote captures this moment of theoretical consolidation. It shows how a single experiment can ripple outward, influencing equations, concepts, and methods. The rotating disk did not overthrow electromagnetic theory, it refined and strengthened it. By revealing motion as the key to magnetism, it helped unify electricity and magnetism into a more elegant and powerful framework. This unification would later prove essential for further advances, but even in its own time, it represented a major step toward a deeper understanding of the physical world. Long after the rotating disk had done its quiet work in the laboratory, its influence continued to echo through physics and technology. What began as a precise experimental test evolved into a lasting shift in how scientists understood the relationship between motion, charge, and force. The significance of the experiment did not lie only in what it proved at the time, but in how it reshaped thinking for generations that followed. Its legacy is woven into the foundations of modern science, often unnoticed because it has become so deeply integrated into accepted knowledge. One of the most enduring impacts of the rotating disk experiment is its contribution to the modern view of magnetism as a relativistic effect of electricity. While Rowland himself did not frame his results in relativistic terms, the idea that magnetism arises from moving charges paved the way for later insights. When 20th-century physicists developed the theory of relativity, they recognized that electric and magnetic fields transform into one another depending on the observer's motion. This profound realization rests on the same conceptual foundation established by the rotating disk. Motion matters, and it matters fundamentally. The experiment also influenced the understanding of matter at smaller scales. In atoms, electrons move around nuclei, creating tiny currents. These motions give rise to magnetic moments, which underlay the magnetic properties of materials. The idea that such microscopic motion produces magnetism can be traced back to the same principle demonstrated by the rotating disk. In this way, a macroscopic experiment helped illuminate microscopic behavior, linking everyday physics to the structure of matter itself. Technological progress further amplified the experiment's importance. Electric motors, generators, and transformers all rely on the interaction between moving charges and magnetic fields. While these devices were developed through practical engineering as much as theoretical insight, their operation is best understood through the principle that motion of charge creates magnetism. The rotating disk provided early experimental confirmation of this principle, strengthening the conceptual bridge between theory and application. Modern technologies, from data storage to medical imaging, are built on ideas that trace their lineage to this foundational understanding. The experiment's legacy also lies in its methodological lesson. It stands as a reminder that transformative discoveries do not always require elaborate apparatus or exotic conditions. Sometimes, progress comes from re-examining familiar concepts with fresh eyes. The rotating disk was revolutionary, not because it introduced something entirely new, but because it revealed something familiar in a new light. It showed that motion, a concept long understood in mechanics, had profound implications in electromagnetism as well. In the culture of physics, the rotating disk exemplifies the power of precise questioning. Rowland did not attempt to solve every problem at once. He focused on a single issue and pursued it relentlessly until nature provided a clear answer. This approach has become a model for scientific inquiry. It demonstrates how careful isolation of variables and disciplined reasoning can lead to insights that reshape entire fields. The experiment reminds scientists that clarity often emerges from restraint rather than ambition. The educational impact of this legacy is subtle but pervasive. Students today learn that magnetism is produced by moving charges almost as a matter of definition. This idea feels natural and obvious, yet it was not always so. The rotating disk helped make it obvious by providing concrete evidence. Its lesson is embedded in textbooks, lectures, and demonstrations, even when the original experiment is not explicitly mentioned. In this way, its influence persists quietly, shaping understanding without demanding attention. The broader philosophical significance of the experiment lies in its affirmation of unity in nature. It showed that seemingly distinct phenomena could be connected by simple underlying principles. Electricity and magnetism, once treated as separate forces, were revealed as intertwined aspects of a single reality. This unifying vision has guided physics ever since, encouraging the search for deeper connections between different domains of experience. The rotating disk thus belongs to a tradition of experiments that reduce complexity by revealing hidden order. Finally, the lasting impact of Rowland's work can be seen in how it reshaped expectations about explanation. It taught physicists to look beyond surface descriptions and ask what truly causes an effect. Instead of accepting that certain devices produce magnetism, science learned to ask why they do so. The answer, grounded in motion of charge, proved both simple and profound. This shift in explanatory style continues to influence how new phenomena are approached and understood. The seventh keynote captures this enduring legacy. The rotating disk that once challenged accepted physics has become part of the background of modern understanding. Its lesson, that motion of charge gives rise to magnetism, now feels inseparable from the way physics describes the world. Yet remembering how hard won that lesson was offers a valuable perspective. It reminds us that even the most familiar truths began as questions, tested by careful experiments, and secured through persistence and clarity. In that sense, the rotating disk continues to turn, not in a laboratory, but in the ongoing evolution of scientific thought.